Yeah, hello, welcome to the webinar about the introduction to application works. My name is David Kalibe, and I will explain you in the next hours the basic functionality of the workflow of development of applications with our chemometrical tool, application works. Yeah, that's already opened here, and let me first explain the main two tabs of the software. We have here this workflow tab and an option tab. In this option tab, the main function is to set the database thing, settings. For example, you could here select a server and the user and the database to access the data that already stored or to store the new projects. So that's then moreover you have here some settings to do backups of your database, but this shall not be the topic of today. So let's go back to this workflow of the software. This goes from the left-hand side to the right-hand side. It starts here with managing your projects. Then it goes on with collecting your samples, organize them, introducing reference values, connect them together, and prepare everything required for the calibration development. As soon as this is done, you go further here with the calibration development itself. That is basically clicking this calculate button, and then a new wizard will start, which guides you through the process. And as soon as this is done, you could combine for certain things your calibrations into an application, which is nothing else than a container holding the different models to do a multi-component analysis on one spectrum. Yeah, so let's start with this project. Here, if you click on this Manage button, you will find here this Manage Project dialog. So far we see we have two alphabetical ordered projects. This customer A, that's some projects from the past. Then every database has this startup project from the very beginning. And now we want to create our new project to develop a calibration model today. Therefore, click here on New Project and give this project a name. I call it now Webinar. Webinar. And if you like to, you could put here a comment so that you later on know where or what this project was about or is about. So let's call it Webinar from 9th March 2018. Then click OK, and then you will find your new project here in this list of projects. You have some more options. You could edit such a project, which basically will show the same information to be edited as before. And you could delete projects if you don't need them anymore. Then every sample, every calibration, every application which is inside this project will be deleted. Or you could select it and open this project. So now you see here in our project explorer, which shows all the data which are inside this project, that the heading is webinar. Yeah, that's more or less everything about this. There's just some shortcut button, this new, which will just create new projects. This exit button will exit the software, but we want to go on, so we will not click it right now. So now it's time to get samples into our system. Of course, first of all, you have to analyze some samples with the spectralizer. This is required because this NIR technique is a secondary method. That means we need, first of all, reference values from a laboratory, which we could then connect with our spectra, calculate based on this by multiple linear regression, the so-called calibration models, which then could be put into the instrument for prediction of unknown samples. And that's basically what the software is for, and what we will do right now. I had already sampled some some spectrum before. This was some milk powder, and now we want to import the first batch into our software from the hard drive. Therefore, we have to select this batch. Let's start with this milk powder small AWX3 file. Click on open, and then after a few seconds we will find this batch here in our project tree. This was so fast because, as you could see, this batch contains only 19 samples. If you click on this plus button, this will expand this batch and you will find all the sample names here in this tree. And if you select one individual sample, double click on it, a new view will open that shows you the information of this individual sample. You find here the name of the sample, which identifies this sample and allows the relation to the reference values later on. You will have here sometimes some UUID, which is currently undetermined. This identifies this spectrum uniquely. This path length is related to our other instrument. This is now measured with the spectralizer 2. But if you have a spectralizer grain, which analyzes in transmission, this path length is of interest, and this will be noted here. Then here could be the serial number, which is for this instrument 110. Somehow it's not independent from theory. You could enter this, or if it's stored by the instrument itself, then you will find it here, but it's not inside this batch because they are a little bit older, the data. And if you like to, you could annotate something to the sample. Moreover, you could have here properties if they are assigned already to the sample. And you find here a plot of the spectrum itself in absorbance units. So for every filter you find there some absorbance value. So that's the view of the sample. Let's go on with the batch itself. If we open this by double click, this batch view is shown. Once again, we have some general information about this batch. Here is the name. It's called here milk powder OR. Maybe we rename it to the name that the file had, small, because this is a small batch of just 19 samples. You find here the timestamp when the batch was created. Then here the commodity. The samples are from milk powder. It's already noted here inside this. If not, you should mention this so that you know what product you are working with. You could enter here the operator name, for example mine, David Kaliber. Here you could put in your company name, or maybe the name of your customer's company if you're working for a customer. Then you could do here some annotation about this batch. You could enter here the serial number of the instrument which this spectra were collected. You have here the presentation mode. In this case it's closed cap, but there are several other modes available, mainly everything which are available on such a spectralizer 2.0, which is named here as the instrument with which this data was captured. After you change this data, you have to click here on apply to store the changes into the database. So now the data are stored. Then you find here a second tab which shows you the spectra of all the 19 samples. That might be quite helpful to identify some samples which had problematic spectra. Maybe you accidentally started the measurement without putting in a spectrum, or you measured a reference disk in between, and then you could figure out the spectra that does not match to the others and remove them by this way from the batch later on. Therefore you could go here with the mouse, for example on this spectrum, and then you find there the sample name, and then you go back to the list, find this sample here in this list of samples. In the first column is the sample name given, select it and delete it. In the second column you find the timestamp when the individual spectrum or sample was measured. So next we could go to this button bar, which has a lot of tool buttons, which allows you to manage the data inside this batch. If in the front you find the information about how many samples are inside this batch, in this case 19. Then the second button is used to import reference values from a CSV file, a very helpful tool or button. This button could be used to split this batch into several batches to divide the data. Here you could delete samples, therefore just select several ones, click on this button, and then you will be asked if you really want to delete them. If so, click yes. We don't want to do it, so click no. The next button is to do an offline prediction. That means if you have already some calibrations inside the database, then you could use this to predict unknown samples. This will be demonstrated later. Okay, there was a question coming from the chat. Someone wanted to know if we could zoom into the spectra, and yes, this is possible. Therefore, you could, for example, here in this case, or here's some activity. You could just move such a rectangular around this data, and if you release the mouse, then you will get the zoomed look into the spectrum. Okay, let's go back to the toolbar. I stopped here in the position speaking about the option to predict data, which will be done later. Then we find here a button to export the batch to the database. There you have the option to, on the one hand, to export them back to this AWX3 format, which is coming from the instrument itself too. But for example, if you have already manage the data, then you could save this data once again in an additional file, or exchange this batch with other users of Application Works. And we provide this jcamp.dx file, which is some common spectral format, and could be used by other software tools, for example MATLAB. The next button is to export all this information you find here in this list as a table, and here the main or the most valuable format is of course this Excel format, but you could save this as PDF or TXT file too. This button allows you to bring the spectra into a extra dialog that might be sometimes helpful to have a second window with the spectra. Then you find here a plus and a minus, and this is to add or to remove properties to your project. If you click on this plus, you will see so far is this there are no properties in our so-called property pool, and that means if we want to have a property, and we need properties in our project, we have first of all, or in our batch, we have first of all to add them to this project. for example, protein, and then you have to define the unit in which this is given from the reference lab, percentage, and the accuracy, that means the decimals behind the point. So that's maybe 2 here. Click on OK, and now you find here in the list a new property. And if you select it, click on OK, you have this here now in your batch. And this none means not a number. That means so far is no value assigned. So, but we want to have a second property, because we have not just protein from the reference lab, we have moisture, and we have fat too. So once again, click on moisture to edit, and yeah, that shall be enough so far. Now I show you how to change the value. If you have the values from, yeah, on a piece of paper from the laboratory, you could use this batch view like an Excel sheet, just editing this individual results. For example, 12.5 for protein, and 10.4 for moisture, and so on and so on. It's a lot of work, and if you have some more luck, then your reference laboratory provided you an Excel sheet with all the reference data already inside. And in this case, that I will show later. First of all, I want to explain this last 3 buttons here. There's this minus to remove such a property, for example, this moisture. Just click on accept, and then you will be asked if you really want to permanently remove it, because as you could see, if I click yes, then it's completely gone, and all the reference values that we just entered are removed too. This button is just opening this property pool that we already know, where you could add new properties like ash. So that's known. And here we have this to arrow button is to replace one property by another, for example, protein by ash, or vice versa. As you could see, here is now ash instead of protein. And now let's bring it back to protein. That is helpful, as you will see right after we imported reference value from a CSV file. This last button is only useful for continuous spectra, as we have this for the grain machine, and thus I will not talk about this today. So let's prepare our Excel sheet for import. As the button here already says, we need a CSV file, that means a comma separated value file, and therefore we have to go here to our disk. This Excel sheet here from milk powder references that were provided to us by the lab. We can open this with, for example, the tool LibreOffice, and then you find here such an Excel sheet inside, and the lab gave us the data. Here in the first column is a sample ID that should be the same as in Application Works, in the Application Works batch view, to identify the samples. Then we have here some additional information like the timestamp and the individual references with its values. Application Works expects in the very first column the sample ID, so that's good already. Then in the second and so on column, the references. The header has the first row has to be a header with some, for example, sample explaining that there's a sample ID, and then the property names shall be named. So we have to revise this table a little bit. First of all, we have to remove this timestamp because this is not of interest, and will just application works will not be able to interpret this correctly. So let's remove it. And next, it's a good idea to remove this units, because application works so far cannot handle this in wireless CSV import. So just name it fat, moisture, and protein, and keep in mind the original units so that you could set them up correctly in the batch later on. So as soon as this is prepared in this way, so sample ID in the first column and the first and second and third properties in the second to fourth column, store this as a CSV file. That means save as. Select here in the file format CSV and select some file name, for example milk powder references. Click on save. Then you will be asked if you really want to save this in CSV format. Yes, we want. And assure that this separator is a semicolon. That might help you to get the data in the right way into the software. Click on OK. Then it's done. Close this LibreOffice and go back to Application Works. Now we could click here on our CSV import button and select our new file here, milk powder references, in CSV format. Click on open, and now we will be asked if we want to keep the old value that we entered manually or replace it by the new value. Because the new value is correct in this case, we select the new value. Click on OK, and we will ask for a second time, and because this is annoying and it shall be always the same, we say don't ask me again and click on OK, and then it's just done. And now you find here your protein is filled up with reference values, and we have additionally fat and moisture with unknown units, and this is of course not what we want. We want to keep the information about the unit, and thus we will replace now this fat with unknown unit by fat in percentage. Click on OK, and therefore we could use this button with the two arrows once again for moisture unknown by moisture in percentage. Click OK, and now our batch is completely filled up with all the reference data. From theory, we are now prepared to start our calibration process, but so far we have only 19 samples, and this is too less to get a reliable model. And therefore I prepared a second batch in this data folder, which is called just milk powder AWX3. I select it and open it and import it to the database. You see this import takes some more time. That's due to this is much larger, as you will see in a few seconds. This second batch milk powder has 335 samples, and we are lucky, I prepared it already. If I open it, you find that all the samples have already reference values assigned. So then we have in general everything what is related to batch management done. Now the calibration process could start, and therefore just click here on calculate, which will open this dialog giving you the option to calibrate an MLR model, which is meant, or which shall be used or has to be used with filter spectra from the spectralizer or spectralizer 2, or PLS, partial least square regression models. This is has to be used for the spectralizer grain. Or you could enter manual models, which if you have some old model on a piece of paper from a calibration report, you could enter them here by this option. We want now to recalculate a completely new model for a filter instrument, thus we select MLR and click on OK. This opened this calibration wizard MLR, which shows you all available batches which are compatible with this technique, with this calibration technique. And we could now select 1 or 2 batches, or if more available, of course, even more. Then on the right hand side we find here the property that we want or could calibrate. For both batches we have fat, moisture and protein available, and let's start here with fat. Next we have to decide if we want to ignore samples with 0 reference values. This is the default option, and we could leave it as it is because we have no reference values of 0 inside the batch, so we don't have to care about. The range has to be adjusted. Default is 0 to 100 because most of our properties have percentage as a unit, and thus the range is 0 to 100. Sometimes you have properties which higher levels, then be careful that you then adjust the range to a higher side. Or what you could do too, that you, for example, want to just consider samples in a certain range, for example, with very less fat content, only from 0 to 12%, then you could limit this to a sub-range. This is the MLR settings. That means how many, or what is the maximum number of filters that you want to use. And 7 is always a good choice because if you take more, then you will just overfit your data in general. But if you take less, then maybe you will not find the right wavelengths that has to be used to predict your unknown samples later on. The sophisticated settings could be used to exclude, for example, some wavelengths from your calibration. That might be that you want, for example, you have here your data measured with some premium measure instrument which has all 19 wavelengths inside, and you want to calculate this for some other spectralizer which have just a reduced filter set, and to ensure that not these wavelengths are used which might be better but which are not available, you could deselect your individual wavelengths by just unchecking them. But we want to use all 19 right now. Then there's this pre-treatments button where you could select standard normal variate, but this is just for experimental use and is not supported by our instrument yet. So don't select it if you want that the calibration will work on the system. Thereafter, just click OK or Cancel for sophisticated settings. And then we have here just one last option. This is this do combination search. And I will explain this combination search while the calculation will already start. This will take some time, so I will use this time. Combination search means that in the very first step we calculate for every just for one wavelength model, and therefore we use every 19 wavelengths. So first we take the first wavelength, calculate a model, check the statistics, how good it is, or remember it, take the second wavelength, calculate the second model, save once again the statistics, and do this for all the other 70 wavelengths too. And thereafter I compare my 19 different models, and based on the statistics I select just the best model and discard all other models. So calibration is done, but I will go on with explaining this combination search, because so far we have just one model with one wavelength. Now we proceed in calculating models, or the model for the best model for 2 wavelengths, and therefore we take the first and the second wavelengths, calculate a model, once again save the statistics for this model, take now the first and the third wavelengths, calculate a second model, compare to the first, and decide which is better, and discard the worse one. And so we go on, and this will be already more than 19 wavelengths, because there are several combinations to have 2 wavelengths. The first and the second and third, and so on. And with this procedure we proceed. Next with 3, with 4, with 5, and up to 7 different wavelengths. And in the case for 7 wavelengths, we will, or we have already, or the software has already to calculate up to or over 50,000 different models. And from this 50,000 models, the best, or the one with the best statistical data is kept. And this selection of the 7 best models will be here presented in this calibration dialog here, which we see right now. Maybe let's start here in the very top. There is the model named. This technique is this multiple linear regression, and here are you could select the different components. 5 is the very best model of all the models that we calculated, and but you could decrease the number of wavelengths or increase them. So you see there are 1, 2, 3, 4, 5, 6, 7 different models, and these are the results from this so-called combination search I just explained. Let's go back to the suggestion of the software to use just 5 wavelengths. Next I go on with explaining this right-hand side of the dialog. You will find here this reference range that we set in the very beginning from 0 to 100. You could still limit this in the next run if you like to. You have here the number of samples included. So far no samples were excluded. That means we have removed 0, and we have 354 samples inside. The range is from a minimum reference value of 18.77% up to 27.1% content. Then you will find here the so-called root mean square of calibration and a root mean square error of cross-validation. The difference will be explained very soon. Moreover, we have here the correlation, the correlation coefficient R squared 1. This is from 0 to 1. 1 means very good correlation, and 0 means no correlation. And if this is higher than 0.9, sorry, then you could assume that your model is quite okay to be used in routine analysis. This so-called adjusted R square is coming once again from the cross-validation, and should be in the same, or is in the same range. One more important parameter is this capital F value, or Fisher's value. This is a measure for the robustness of the model. The higher this value is, the robuster is the model, and as a rule of thumb it should be higher than 1000. It's increasing with increasing number of samples, and it is increasing with a decreasing root mean square error of calibration. This bias is just some, it's the mean value of this, or the reference values, and is not of big importance. So then you will find here some buttons to do actions on the samples. You could mark outliers, you could unmark outliers, you could unmark outliers, you could recalculate, you could do some automated improvement by means of some built-in algorithm, but I suggest usually not to do it, especially not in this MLR process, because if you do it on your own, the model will be more reliable for sure, because there could be some human judgment be involved, and not just this very strict computer algorithm. yeah, you could once again open this sophisticated settings dialog to deselect wavelengths later on if you want to. Okay, that means we are now ready to explain all the other stuff, especially what are cross-validation, what is regression, and what are outliers. So in this first tab, you see here different tabs at the top. This first tab we have this regression graph, and this is on the horizontal axis we have our reference value, and on the vertical axis we have the predictions from the models. And yeah, we have two kinds of models. One is the calibration model that will be used later on in blue, and which is almost hidden by the red ones. This is a cross-validation. This cross-validation is not a real validation, it's just yeah, some yeah, pseudo validation, which allows us to get a better estimate for the real performance in the routine analysis, and moreover it helps us to determine the best choice or to avoid overfitting and to take the best choice of components. So this cross-validation is calculated in this way. I divide my complete batch into 20 different subsets, and now I leave out the first subset of this batch and calculate a new model based on the 19 other subsets, and then I take this new additional model to calculate or to predict this first left out section.
Frage ist, wie viele Samples brauchen wir für eine gute Prediction?
Ja, komme ich später zu. Ja, komme ich später. So this, then we have predictions for our first sections. In the next step I leave out the second section and predict a second model based on the first and the 17 following sections, and this model I use to predict the second section, and I go on with this procedure so that I get 20 different cross-validation models, and which each these models I calculate the left out section, so that in the end we have for every sample a prediction which is yeah, somehow independent from all these individual models, but of course are not the same as if we have predicted this with our calibration model, but this gives us an estimate about the performance of our model later on. So these results are plotted here in red, and they are, yeah, more or less the same as the blue ones, the regression ones, and that is why the blue ones are hidden. And then we find here some purple dots which indicates outlier that were detected by the software, and these outliers yeah, somehow do not match to our batch or to our calibration model, yeah, somehow calibration model or into the batch, and thus it might be a good idea to remove them to get a better model, because it might be that this, yeah, for example, if this is a wrong result from the laboratory, or if the laboratory analyzed them wrongly, then this will just disturb our model. Okay, in between we had a question from the internet, if or how many samples are required for a good model, and there's no general answer to that. At least we need, I would say we need 30 to 50 samples for in the very beginning. Maybe if you just want to know if it's a chance to calibrate something, then a little bit less could be an option, but this should not be used for doing a routine analysis. And especially 30 to 50 samples are only enough if you have a easy to predict, an easy predictable product. For example, alcohol in wine might be, if it's just some special kind of wine, just red wine of the region of Bordeaux, might be easy enough to build the calibration up on less samples. In our case, we have here milk powder, which is very different. We have different kinds of powders, which of different kernel sizes or particle sizes, and that means we will need for sure more than this 50 samples. We have here now 300 samples inside this batch, and especially the larger the variety is of the product, the more samples will be required, because all the differences has to be, or the model has to be trained to all the differences that might appear in routine analysis. Sorry. Okay, then so far to this regression graph. Now let's go on with some further tabs before we will be able to do a recalculation of the model. The second tab are the so-called residuals. This is in general the same graph as before, just a little bit differently displayed. Once again, we have the reference values on the horizontal axis, and on the vertical axis we have just a deviation between the reference value and the prediction, the so-called residual, and as a result we will get more or less a 45-degree tilted graph. So you find here on the 0 line the identity that we had before, and then up and below and down the deviations, and it's a little bit easier to figure out the samples which have big deviations and might have wrong reference values, or maybe does not match so good into our batch. Next we will find here this variance graph, which shows you here on the horizontal axis the components. On the left hand side we find the root mean square errors for the cross-validation in blue, for the calibration in blue, and for the cross-validation in red. And you see with each factor the calibration root mean square error decreases and gets its minimum by 7 components. And this is due to, with every more wavelengths we get more information into our model, and this is it's getting closer and closer to the reality. However, it could be that, it is for sure that after some component we will use wavelengths that are not related to fat, they just having some noise or some other components, or some other properties, but we fit them into the special fat model, and then we do so-called overfitting. And therefore we have this cross-validation error, which goes down too in the very beginning, and after some time it starts to increase again. And as a second measure we have this Fisher's value here on the right hand side vertical axis, and displayed in violet. This is increasing with the factors and getting here its maximum at 4 or 5 factors. And as I told before, this Fisher's value should be as high as possible, because a high value indicates a robust model. In this case we have here for 4 a slightly higher value than for 5 factors, and now we have to decide which is the better one. The software, the built-in algorithm of the software says us we shall use 5 factors, although this 4 factor model has a higher Fisher's value. But this is some kind of trade-off of having a robust model and having a low root mean square error. And here comes now the experience of the calibration developer into play to decide what is the better one. Let's decide for 5, because the software proposed that, and the difference is not very big between the two Fisher's values. So the next thing is the sample distribution, which shows you here the reference values once again on the horizontal axis and the sample count on the vertical axis. And we will find here several bins, and for each bin the count of the samples within this bin. For example, here for the range between approximately 18.7% of fat till 19.5% of fat, and in this case we have 90 samples, and this is for every bin given here, and this allows you to identify first of all if we have a representative sample set, or if we have to collect more samples in a certain range. Usually this tends to be some kind of normal or Gaussian distribution with a maximum in the middle and a very narrow band, and in the outer ranges almost no samples. This is here not the case. The optimal case would be having for every bin the same number of samples. In this case we could have some more samples here in the range between 19.5 and let's say 22.5% of fat content. So here could be more samples collected to improve the model. On the next tab we find the model itself. The wavelength is here on the horizontal axis, and on the vertical axis we find the regression coefficient. And for every wavelength or filter that is used, we find here a dot. For example, here for the 1680 nanometer filter, the regression coefficient is minus 184. This is given for all the models, and if you like to, you could see here how large are the coefficients. They shall not be too large, otherwise the model might be sensitive for noise and thus not stable. Now we come to a very helpful tab, this outlier graphs. We have here 3 different outliers for this MLR models. The so-called age or leverage outlier, which gives you here for every sample a certain value, and the black line indicates a threshold, and if this threshold is indicated we speak about an outlier. This age outlier gives us is an indicator for the influence of the sample on the model, and this might be a good influence or this might be a bad influence. So due to this reason we shall not just remove them just because they are outliers, because maybe we remove important information. The second graph, it's organized more or less the same, but we have 2 thresholds, a positive and a negative, and this is a t-outlier based on the student's t-test, and it's almost based on the residuals. So that means if we have big deviations between reference values and predictions, then we will find here an outlier. And so if you just want to reduce the root mean square error, it's always a good idea to remove these outliers, especially if we have a sample that does not fit in the model, then it will be detected as t-outlier. And last but not least, we have this D or Cook outlier, which is a combination of the age and the t-outlier. That means if we have a H outlier, which is a D outlier too, which is in this situation not the case, then we shall remove this H outlier. Otherwise, I would leave this H outlier always inside the set. So in this case, we have here this T outlier, for example, and this one, which are large enough to be removed in the first step. Thus, I click on it to mark them. As a rule of thumb, do not remove too many samples in one iteration step, only 2 to 3, and never remove more than 5% of the samples included. That means in this case, not more than 17 samples. So then we find here our outlier, or so-called outlier list. On the left hand side we find a list of all the samples inside our calibration. And on the right hand side we find removed samples, which is currently empty because we did not remove any models so far, and we have for every sample a reference value. So then you will find here in this outlier list that some of them are black, other are red. Red are them which exceed some of these thresholds. For example, here this number 84 is red and is already checked because we selected this in our outlier graph. And you could use this check boxes to remove samples in the next run, independently if they are outliers or not. We want to remove just outliers in the first step, so we unmark them once again. So before we do a recalculation, let's have a look here on the spectra tab, which gives you all the spectra in the batches or included in the calibration. And it might help to identify samples with some mismatching spectra. If you once again go over such a spectrum, you will find the sample name, and then you could identify the sample here in the list, check it, and remove it in the next run. And the last tab gives you a history, which shows you here the iteration steps on the horizontal axis, and on the vertical axis in the upper graph the root mean square errors, and in the lower graph the best number of factors the software detected. This is of course in the very first calculation step very boring because we have just one step. So now we are prepared to do a first recalculation. You see here our samples are black because we selected them before. If we now click on recalculate, a new model is recalculated in the same way as before. The only difference is that these two black selected samples will be left out. Okay, and after some time we have the new result. As you could see, the black marked samples are disappeared. And if we have now a look first of all on our outlier and removed list, we find here the two samples that we just selected before. If we like to, we could now select them to bring them back in the batch in the next run. Or we could select from our outlier graph further outliers. I would say those are not so good, so let's once again check 2 and yeah, do the next recalculation. So now we have our third model, and let's now have a look into our history. You see here the iteration of first, second and third calculation step, and with each removal of outliers the cross-validation error is reduced. And here we find the best component with stays 5 over all iterations. So here's our regression graph, and from my point of view, this looks quite good. Although we have still some outliers inside, we could think about removing this one here. But I guess this will not change much the model. Mostly it will just optimize our statistics and might promise to good performance than we will find in the routine analysis. Because such a sample might occur in later on, of course, once again, and then the prediction will be the same independently if we remove it now or not. And then the user might be disappointed because the model is not holding what is promised. So now it's time to save the model to the database. Therefore, click here on Save. This will open this dialog where you could name the model. That should be a unique name, for example, or some explaining name. Milk powder is good because it's milk powder. Fat is a property, and maybe you put there something like the date, 2018, March, and it's the 9th, so that you know this is the model from today. And now you have the option to save the history. That means the 3 iteration steps and the different settings we had. Or you could discard them if you are not interested in the future. This will save a little bit space in the database and increases time for storing. Let's keep it checked and click on Save. Okay, now it's done. We find here a new calibration model. So now it's time to have a look into this. Therefore, double click on it and this will open this calibration view, which is divided basically in some different tabs once again, and here some regions with general information which give you the name. Some of them could be edited. That means you could now, for example, if you like to rename the model or not, you could here change the commodity. Maybe you want that it's in capital letters. You have a timestamp which let you know when you calculated it. You could do an annotation, model calculated while webinar. You have here the property that might or could be changed, but this will, first of all, it will have somehow will corrupt the relation in the database, and moreover, if you change fat to protein, you will have the problem later on that the fat model predicts protein, and this will not match, or will not match or give you the right protein results, of course. So be careful. Only in cases if you have, for example, fat in English in this original version and you want to have this in some other language, for example in French, then you could change this French fat property by the English fat property by the French one, so that you do some language adjustment, and then it of course will work. But this is the only reason why we could change it. Then here could be the instrument set. Spectralizer and Spectralizer 2 are compatible to each other. 2.0 is the actual version, so let's change it to this. Here you could set the presentation mode. This was closed cap. Here is the model type that we used. Then you will find here a unique ID which identifies this model uniquely for the Spectralizer. And you will have a version. That means if we recalculate this model by this button, because, for example, we have new samples available that we want to introduce, then this version will be increased. And if we import this model later on to our Spectralizer, and it was already there with some previous version, the instrument will know that this file shall replace this calibration with this unique ID by the higher version. Or if we try to import a model with a lower version, then we will be asked if we really want to downgrade our calibration. You will find here all the components that were calculated. So still now we could export different number of factors. We don't have to decide us for the best one that we stored. This is named here so that we know this still. We have here some kind of bias which might be used from bias Q adjustment. This is the original bias and which is valid for the instrument on which we calculated it. This Q is always 1 in the very beginning. Then we find here some buttons. The recalculate button, as I already mentioned, we could recalculate the model. We could click on report, then we will create such a PDF file, therefore all the data are loaded to recalculate it one more time. And then we get here such a nice PDF having all the important information inside. What is the model for, the calibration name, which application works version were used, how many components were considered, what is the algorithm, what was the best number of components, the selected one, then the property for which this model is, and the unit. The regression graph that we already know is plotted into this report. The root mean square errors are there, the R-squares, and the Fisher's value. Moreover, we have plots of this variance graph. The model that we selected is plotted too. And we find here how many samples are inside, the minimum and maximum, and the mean value of this samples of the batch. How many samples were excluded while calibration development. We find our sample distribution of the batch and the residuals. And moreover, the explicit model is named too, the bias, the wavelengths that are used, and the wavelengths coefficients are printed here too. And for example, if you find such a piece of paper, you could use them to enter this manually into a database if you don't have it so far there. And then it's named which batches were included into the calibration and with how many samples they are represented in the calibration. So this document could be printed or saved somewhere or distributed to colleagues or partners. Okay, then we have here once again access to this property editor that we already know from the batch batch view. For example, you could now introduce the German property for fat. It's similar written but different. Fat. The unit is still percentage, accuracy is 2. If we do so, now we find it here, and now we had the choice to select to change here fat in English to fat in German if we like to. That's what I meant, spoke about before. Let's go back to the English name so that everyone understands what I'm talking about. This adjustment button I will explain later. This is for bias and skew adjustment I already mentioned, and because I changed here a lot to the settings, I should click on apply. Okay, sorry for the short interruption. So now let's come to the statistics. They are here printed below. There's once again the minimum, the maximum, and the mean named. We already know all this data. We have the used samples, the Fisher's value, root mean square errors, and there are squares. And as you could see, they are changing with the components. And let's go back to our best model. And if we hide the statistic, we have space to show our batches that are inside. We have here the model for the different number of components. And if used, for example, this standard normal variate that I suggested not to use, then it will be named here that this is part of the model. We find here some buttons, one to add samples, or yeah, there are no additional we could add, so that's why it's empty. But if we here click the minus and remove some samples, for example the first 3, and click on OK, then we will find that the number of samples changed, and if we now click on plus, we could introduce them. That's the way how we could add new samples in our calibrations. But if we do so, we have of course later on to recalculate to get the valid model for this settings. Or we could directly remove by this. If we select here milk powder, click on minus, then it will remove the complete batch. If we click OK, if we click on cancel, it will stay inside the collection. Then there are 3 more buttons, 2 for saving data, or all are for saving data. The first is to export the model into an XML file to be used on Spectralyzer. We have one for saving all the samples that are used in our calibration and that are not used into a file. If we do so and go here to data, we will find here this milk powder fat file, and we could have a quick look into this with Notepad editor, and you'll find here used samples and all the names are there. That might be useful for evaluating or writing reports on it, and the one that are ignored, so that you have an overview later on which samples are involved in the model. And then we have here this export button, which allows you to store all the spectra in one file that are used for the model. In this case, that would combine these 2 batches, milk powder and milk powder small, in one batch. Yeah, some special button which might be helpful, but usually is not used. Okay, so far to this overview. Now we could have a look on the other tabs. They are already known. We have once again the variance graph still available. We have here the model graph, which we could go through. And we have this regression graph, which has, you know, the warning that we have to recalculate the model. That's due to I changed property and the number of samples in between, and so it's not, you know, it let us know that we shall click here this recalculate button to apply the changes to the model that we have, because this has nothing to do maybe with the settings we have right now. Okay, that's all to that. Now we could use the model to do predictions, and on the one hand, and this is a normal case, we could export this model to the hard drive on the one hand as AWX3 file for archiving it or to exchange this with someone else who uses application worx, or we want to put this into, is the usual case, on our instrument for analyzing. So select Spectralyzer 2.0 model and give here some name that you want to have, click on save, and then this dialog will be opened. This is the calibration name in the very first line, which will be found on the instrument, and yeah, that should be unique so that you could identify the model by that. Here is the product of the product database on the instrument, so this is mostly used for organizing it. Be careful that if you want to combine several models in one product, that you spell this always the same, otherwise you will mess up your database. Here is the unit that's taken directly from the database, which will be used on the instrument and will be shown later on while in this analysis screen. You could introduce a temperature in the calibration file, but this is currently not checked. It's just an information for the user. The same applies to the closed cup. That's the presentation mode, so that you know later on your system which presentation mode should be used. You could select here some country where the calibration is from. Here it's from Germany. You could name the company who owns this model. This is ZEUTEC. And you could enter here some annotation that you will find on the instrument too, so that you know maybe that's experimental model or the model here from webinar. And the range that is used is written into the file too. And then from the past we have this compatible to versions lower 2.14. Nowadays every instrument should be updated to at least 2.17, in best case to 2.18. And these versions are compatible with this new feature, unique ID. If you have, or if you would have an instrument with an outdated software, lower 2.14, then you will not be able to import this file if this is not checked, because the unique ID is not handled by the software versions. So if everything is as you want, click on OK to save it. So now we have exported our model, and if we have a look in our data folder, we find here this milk powder fat XML file that could be now copied on a USB or a web folder which is connected to the instrument, or it could be imported by and then imported by USB files through the software, or you could use the web server for importation. In the next step, we want to do an offline prediction, and therefore first of all we need a container which holds our model. Therefore this container is a so-called application, which is in the context of Spectralizer 2 only used with application worx. First of all, the application needs a name. Let's call it milk powder because it's for milk powder. Then we will have here the timestamp of creation. We could annotate it if we want, and we have to specify the commodity. That's in this case milk powder 2. Then the default instrument is Spectralizer G, that means grain, because for this system this is still required for export, but we want to use filter spectra. That means it must be changed to Spectralizer. This application has a unique ID too, and thereafter we could apply the changes to our application, and you find here below a list where we now could drag and drop models inside. So now it's there. Milk powder fat could be analyzed with this application. You could use this plus and minus to add further. Now we have no further, so you cannot, or you could remove this once again and now add this. So that's where this this plus and minus is for. This export button is to export such a calibration, but this is only for grain applications useful. Now we are prepared to do an offline prediction. The only thing we miss is a batch that we could predict, and this could be once again imported from such a file. Let's take this Validierung or validation batch here, import it. Now we have it, and you find here once again a batch similar to the others with reference values, and now we could use this predict button, this small calculator. Click on it, and this opens this offline prediction dialog. You could select application, and now you could click on do prediction. This is our milk powder application, by the way, that I just created, and you find here our offline predictions by the model. And you could now compare this to reference values, and now you see there's fat, and you don't know what is the model, what is the reference lab. And then if you click on model name, you find now here milk powder fat, the calibration name that we used, and fat, and now it's cleared where the data are from. And you could now compare your predictions from the model with the ones from the references, and here for the first 3 samples that are always, they are quite close, so this looks very good, and even the others are quite promising. And in the end you get here some root mean square error of prediction, so the validation error of this batch, and a bias if so, but this is 0 in this case, and a standard error of prediction, whereas the bias corrected root mean square error of prediction. So if you like to, you could export the results for further processing by Excel. Therefore we provide text and CSV files. The CSV files could be imported by Excel later on. I need a file name, predictions, and save it. So if work is done, you could close the dialog, and this was the application of our new model to unknown data, which is usually done by the spectralizer itself. Last but not least, there is the not unimportant topic, adjustment of a calibration. The thing is that every instrument has its custom characteristics. That means every spectrum, although of the same sample, is slightly different due to small changes in the optics. And this is especially valid for filter instruments, because every filter is different. They have not all the exact same wavelengths, and the transparency of every filter is slightly different too. As a result, you will observe, if you have now your model calculated based on the spectra of your instrument A, and put this on an instrument B, so a different instrument, that you will not get the same results as for instrument A. There will be some bias, some offset of the data, the results, and this is due to the differences. And to overcome this, we have this bias skew adjustment. That means if you want to apply your model on instrument B, you have to do this adjustment, and therefore first of all measure a set of 5 to 10 samples with known reference values. This is already prepared here, and we import this so-called adjust AWX3 file. Once again we get a batch, and this is already filled with reference values. Now we take our model that we calculated on instrument A and click on adjust and select our adjustment batch from instrument B. Next we click on perform, and we get here now 3 different curves. Black is hidden by blue more or less and is the original, so just predicting or using the model as it is. Blue is only a bias adjustment. That means we shift the model by a constant up and down. So that means if, for example, all our reference predictions are 5 too much, we subtract just a bias of 5 from our results and everything is fine. And red is a bias and skew adjustment. That's not just an offset to shift, it's also that we a little bit tilt the model. That means that we shift the lower values in a different way than the higher values or in the middle. This shall be only done if we have more than let's say 5 samples. I think 5 to 10 should be available over a reasonable range, because otherwise you could around one point you could almost tilt it in any angle, and your bias skew adjusted model will not perform good. So be careful with the bias skew adjustment. In any case of doubt, just do a bias adjustment. So here on the right hand side we have the statistics related to the data. If we click on here or select bias only, we will find here for the adjusted model the bias values, the bias and the skew and the root mean square error. And on the left hand side the original, so the unadjusted model, and you could compare it, and you see that in the adjusted case we have a slightly decreased root mean square error, and this is what we want. If we select bias and skew too, then it's even more reduced because we tilted the model a little bit. So let's choose this, click on save, and now we have to give the adjusted model a name, and then it's a good idea to keep the name of the original model and maybe name it BA for bias and skew, and give the serial number of our instrument B, and this is 110002, and save it. And now we have here a second model. If I expand this a little bit, you could see that there are different names, and now we could export this once again as XML file and place this then on our instrument 110002, and then it will work on this machine. These are the same settings as before. This was just here our company name, and here is the comment bias and skew adjusted for 110002. Save it, and now it is ready to be imported by the instrument. Okay, that's the way it works. I explained you first of all how to manage projects, how to get the samples into the database, how to handle the data inside the batch, how to assign reference values, which will allow you to calibrate a certain property. In this case it was fat for milk powder, and later on to apply in application works such a model to an unknown set. Yeah, that's was everything I wanted to explain today. I think now I will stay a little bit online. If there are some questions, you could ask them within the next minutes over our YouTube chat. Yeah, and then I will come back, yeah, or I will be back as soon as there's a question.